Which one? Click. Okay. Good morning, everyone. This is a distinct honor and pleasure to be here to address you, and I would like to thank the conference organizers for putting together this wonderful event, many interesting talks. I look forward to learning all the work that is being done. And yesterday, I arrived to your wonderful city, and I received a very warm welcome, had a nice tour, and I hear it's also unusually warm weather, so that's good. So today, I will talk about neuroergonomics, and that uses wearable neuroimaging and increasingly portable and mobile sensors. And we use specifically optical brain imaging, that is the near-infrared light to monitor brain function with these wireless mobile sensors. And I will talk about how we use them to better understand the human experience, and in this context, the user experience. So before we start, here are my disclosures. I have pending and granted patents and also equity in multiple startups related to brain research and brain medical devices. Okay, let's get started. So some time ago, a wise man said, the chief function of the body is to carry the brain around. Indeed, our brain is the center of our identity. All our thoughts, feelings, perceptions, everything that makes us us is actually coming from the brain. And with this neuroimaging, we want to better understand this organ. And I will talk about how to bring your brain into the picture. So this is pun intended. We're capturing photos and images of the brain, but we want to incorporate the brain information into the equation of evaluation and assessment of complex tools, technologies, and even human-to-human interactions. This is basically true. Yes, the body gives a lift to the brain, but it is, I think, much more than that. So our body is our primary interface to the everyday world. How we discover our environment and talk about discoverability. So that's why neuroergonomics aims to study not only the brain, but also body in a continuum, and we will talk all about that. But first, let's start with the brain. So this 3-pound miraculous tissue, it's a soft jelly swimming inside our skull. It's an amazingly complex machine. It's the most complex machine in the known universe, and it continuously evolves. Everything that we do changes the brain, the things that we learn. We have this approximately 86 billion neurons that are making connections, generating trillions of neuron-to-neuron connections within the brain that are constantly being adapted. And everyone, we have a fundamental architecture of the brain, but everything that we do, all right. So everything that we do changes the brain. So like our faces, we have unique brains. So that's basically an amazing feature, and all the complexity in the neuron network is several magnitudes greater than the whole World Wide Web. So we carry this around with us all the time. So you're seeing here a beautiful micro-etching artwork by Dr. Greg Dunn at University of Pennsylvania, and this is in permanent display at Franklin Institute in Philadelphia. It's a world-class science museum. If you haven't visited, I highly recommend visiting. And Dr. Dunn explains the goal of the self-reflected to elucidate the nature of microscopic behavior of neurons that gives rise to consciousness, this whole experience that we go through. And indeed, a lot of the neuroscience field actually aims to understand that molecular and individual, like cellular dynamics that happen in the microscopic world. And that has been studied a lot. But today we will go the opposite journey, the whole brain, and how we capture information from this brain. And we will talk about functional neuroimaging. So structural neuroimaging is taking the picture of the brain, like the maps of streets. But functional neuroimaging is looking at the traffic over those streets. So we will talk about how we use that information to understand our experience. Okay, so we want to monitor the brain in everyday life. This is a big step from traditional neuroimaging that is done in restricted everyday, like in restricted settings. In everyday life, we do many things. So what do I mean? Workers, warfighters doing their actual tasks, surgeons in the operating room, or students in the classroom. So anything and everything that we do, not only working, but also resting, relaxing. So can we monitor the brain function in all these diverse settings? So this is already underway, and I will show you actually examples of technologies, projects, and approaches that is already accomplished, and many labs around the world is pushing the frontier in terms of technological limitations and how to overcome them, and enabling these technologies more readily for new applications. So speaking of the need, the neuroscience research, there's this tremendous work in looking at resting state brain areas. And what happens when the brain is just resting, doing nothing? And if this set represents the entire space of mental states, resting state is just a small blip within this big spectrum. And we talk about controlled task-specific states. What I mean is when the person is doing one particular task at a time, and there has been growing body of literature around that, and each of those represents separate small areas within this big set. But we are still missing this large area that is the everyday life, these natural tasks that we do in typical tasks. So I call this as the dark matter of the cognition. So what are those, right? So this can be a surgeon during an actual operation. This can be a pilot during the flight in the aircraft up in the sky. This can be a first responder engaging with the fire during that critical moments. Or this can be a student just listening to a lecture in the classroom. Or it can be a lecturer or presenter like presenting. Or it can be the attendees just trying to listen or checking their text or messages, and etc. So all these could be the areas of the mental states that I represent here, because up until very recently, we had no technology to capture those unique aspects. And mobile neuroimaging is opening this door. So we now have more and more capable sensor systems, approaches, and data analytical approaches that enable us to target this. And that gives rise to neuroergonomics. Neuroergonomics actually evolved from, in the last century, from the design of tools, technologies, and it takes expertise from interdisciplinary domains, from neuroscience, from ergonomics, but now psychology, engineering, and many more to actually put together all these perspectives to better understand the human experience. And to make the point of how this technology evolution happens, we need to look at another technology, like computers. So I'm seeing a lot of students, they are too young to understand, but this is the computers. One of the first general purpose computer was developed in Philadelphia at University of Pennsylvania. And this whole room was the computer. And it weighted, this ENIAC weighted 30 tons. It contained 18,000 vacuum tubes. And it was making amazing calculations, like counting from 1 to 5,000 in 1 second. So right now, a lot of the cell phones, the technologies that you have is way beyond that. But you can see even at that early stage of the computer, there were visionaries like Licklider that imagined that there are similarities between the computer and the brain. And like legendary von Neumann, they understand that they're both information processors, but they have complementary skills. And the Licklider proposed that human brains and computers will come together and think as a much more capable unit when they're working together. And today, you can dismiss this idea easily, but it was a far-fetched idea then when you see the computer as a whole room. And also, right now, even we delegate a lot of our cognitive tasks to computers. No one is remembering all their friends' cell phone numbers anymore. They're all recorded in the phone, or a lot of your notes, all the information. We're already delegating to the computers. But it is now not a far-fetched idea to imagine a future where neurotechnology actually augments our cognition directly by interfacing with the brain. So I would like to bring up another giant, Professor Paul Fitts, that made gigantic contributions to the human performance theory. And those students may already know the Fitts law, right? That he basically quantified this regularity of the human behavior, basically calculating how fast someone can move from one point of like a touch screen to another. Why this is important? This came from after the World War II, when pilots in the aircraft are making too many errors. And it's realized afterwards that actually the cockpit design needs a whole revolution, because it's not humanly possible to go from one place to another, from one button to another button. So this understanding, this quantifiable human behavior regularity, then it's now we call Fitts law, defined how the cockpit should be designed, and still today. Another giant that I want to mention is Professor Michael Posner. He made huge contributions to the understanding of the brain and the relationship with the cognitive function. A lot of the key functional neuroimaging studies, and specifically he defined this attention circuit and how it is impaired in different clinical kind of conditions like mental health populations. So a lot of the foundational work actually starts with that. And then I would like to highlight Professor Raja Parasuruman, bringing all this together from the behavior, from performance theory, and the understanding of the brain. He actually postulated that we can put together much more effective human-technology interaction if we incorporate the brain, because fundamentally it's the brain that is interacting with all those different technologies. So he is the founding father of Neuroergonomics initiative that we are still seeing is growing, and we are pushing the frontier with that. Unfortunately, he passed away too early to see this, but he predicted a lot of these very early when the technology wasn't there, like early 2000s. But now the neurotechnology is there. That is accomplishing his vision. So where do we go next? I would say the key next step is the routine assessment. How can we capture the physiological and neurophysiological information fast and routinely? And this is already happening with wearables, with physiological signals, right? There are consumer-grade systems all around that can monitor our heart rate variability, and many other information. But you may say, that cannot be useful. It's very low-cost sensor that may provide a lot of noisy information. But in fact, we can get very useful information even from that kind of data. And this is an example, actually, researchers at NIH, All of Us project, they put together this amazing paper describing how we can get very useful information from this low-cost Fitbit-like sensors, but they are in large numbers, like 200,000 people's data can come together, provide us very pristine information. So these are some early examples, but there's nothing like that until very recently for for brain. So imagine what we could learn about the brain if we could monitor the brain over days, months, and not just short, discrete, like half an hour, but from also hundreds of thousands or millions of people's brain data. So technology is one barrier, but that's also changing. And this is an example from my lab at Drexel. We developed the world's first portable brain imaging device for hematoma detection. This is detecting bleeding after an accident. And this is already doing a task that only room-sized neuroimaging system could do. CT scan, right? That is the only tool. But this can be applied now at the site of even accident or in the ambulance to do this initial triaging so that there's no time lost for the patient. And this is already went through de novo FDA approval and in use in many countries now. And still, there are new developments are happening. But this is just one example. There are many new neurotechnologies that are being developed around the world that are revolutionary, that are doing many things that we are seeing like only possible in our imagination, but now becoming a reality. So that's where neuroergonomics come in place. So now, how is neuroergonomics different than any other discipline? Because we're not just looking at the brain like in the isolation like this. We want to study the brain together with the body, integrated, and in the context of the behavior. So we want to look at this because this is the disciplines, different disciplines have been already looking at this with an emphasis, like neuroscience with focus on brain, maybe psychology focused on the behavior. But with neuroergonomics, we want to look at the whole continuum, brain, body, and behavior, also include the environment. So the same task, the same cognitive task that you do in a serene, relaxed environment is very different than how you do it in a time-critical environment. So we need to understand the impact of the environment. So neuroergonomics incorporates all these approaches, and these are the tool set that we typically use in our studies. Like here on the top left, you're seeing functional neuroimaging that is recording brain activity. How do we capture information from the brain? EEG and FNIRS are the most common variable neuroimaging modalities. And they do fundamentally different way of capturing the brain. EEG measures the electrophysiology, the electrical potential changes over the scalp, and FNIRS, on the other side, measures the cortical oxygenation changes, and they have a lot of number of variations, like I represented here, dry electrode versus wet electrode for EEG, and for FNIRS, we have the flat sensor versus fiber optics sensors. So you can imagine the complexity changes, the size of the number of channels, size of the devices, they all have different impacts. So it's not one size fits all. There are so many variety that means, some of them are suitable for a particular task, some of the others are not. And similarly, on the right top, you can see neurostimulation technologies. These are technologies that can alter or change or modify the brain activity non-invasively. And they work by either magnetic stimulation, they change the magnetic field over the scalp, or they apply some electrical current to excite or inhibit a localized brain activity. So these technologies are used in some clinical practice already, but also in research to create this causal link. What happens in the behavior if you inhibit or excite or some certain region. And also looking at this together with neuroimaging is extremely useful. And then, of course, comes the physiological measures, all the way to eye tracking, and then the motion and movement tracking. So today I would like to focus on optical brain imaging that can actually be used together with all of these technologies. So FNIRS here is the technique that uses near-infrared light between 700 to 900 nanometers wavelength. This is right next to the red color. And FNIRS use wavelengths, either red color or near-infrared range that is beyond our visible domain. And we place these light source and detectors over the scalp to capture brain activity information, like a time series. So we can do this for one location, and we get this time series changes, like from a rest period to a task period. And we can do this also in multiple different brain areas to get a spatiotemporal view, like almost like a 4D video of the brain activity as it engages with a task. Then we can use this information to compare like an easy task versus difficult task, or user interface 1 versus user interface 2, or we can compare between groups, like experts versus novices, or many other different contrasts that may help a certain kind of project. So that is fundamentally the information, the brain activity changes that we get, and that comes from this task execution, the planning. And here are mobile versions of systems that we have been working, some of these like in more than 20 years ago now, at a time that neuroimaging was very new, and we were focused on mobile versions of this with a lot of colleagues at Drexel, Britton Chance, Ban Onaral, Kambis Pruzai, so Kurtuluş İzzetoğlu, so many other colleagues, Günay Yurtsever. So we have developed a foundation of these platforms that became available and then used in hundreds of universities afterwards. So we can monitor not only in the lab, but outside walking and performing regular tasks, and not only adults, but also children, even neonatal babies. And you can see the evolution here from restricted artificial settings to increasingly mobile, and most recently ultra-mobile imaging allows us to go to more and more realistic and actual environment. So instead of like using a low-fidelity simulator, now we could use high-fidelity simulators, and most recently in the actual environment. So these are images with research, actual research from our lab, and the flight simulators, and with the aircraft actually is with Frédéric Dohe from Toulouse, France. Actually, we integrated this neuroimaging into the actual aircraft, and we monitored the pilot as they engage these air traffic control tasks up in the sky, and we compared that to the flight simulator. So now we can do this in literally everywhere, and sky even is not the limit, right? So over the last a decade and a half, we have looked at basic neuroscience aspects, like many different cognitive domains, and this is just a list. And early on, we were comparing this new generation of wearable mobile neuroimaging with traditional neuroimaging, like room-sized neuroimaging. And more recently, as the technology matured, now we were able to move into more new areas that could not be done with traditional neuroimaging, like human-to-human communication or human complex machine interaction. Like you cannot look at the brain activity in real time in a radar engagement, radar screen engagement with an MR machine, but you can do that with wearable neuroimaging, with FNIRS, or multiple individuals communicating, interacting. So these are all new possibilities. But just to give you one example, working memory is a very structured task. It's a paradigm studied in neuroscience, and this is kind of the knowledge is very controlled difficulty levels, and we know that there is this incremental brain activity change as the tasks get more and more difficult. That is, you need to remember more and more items in your working memory at any time. And early 2000s, when we just developed these technologies, we were looking for, how can we test these? How can we show that we can capture information? And this was one of the tasks, and one of the first study out there that we compared working memory, and we demonstrated that using that wearable headset, it's almost like a palm-sized sensor, we can capture the same area, the critical area, inferior frontal gyrus, that fMRI and other PET studies show is the critical area, and we can see this monotonic increase in task difficulty-related change. Later on, we replicated this in many other studies, but this gives us the initial information, and many other labs replicated this information. So starting with that theoretical basis, then we moved on to applied. And we can use the same fundamental information, analytical techniques, to apply this in practical settings, like in aviation. So we have more than a decade of research looking at brain activity of air traffic controllers, UAV ground operators or pilots, and also looking at cognitive changes as they engage with different aspects of this complex technology, and also learning and training, how we acquire new skills, how we learn new features of the tools. So like one study here, one of the first actually now more than 10 years ago that we did was with air traffic controllers, and that was the first study. We took the instruments and sensors out of the lab into the radar environment. And we looked at learning training here as they moved through different training stages, or even the actual flight operation. Here's the BCI that we developed that you can not only record, but even in real time assess the mental state. So these are some examples of human-technology interaction. And most recently, another study with Lockheed Martin, we looked at using the brain information to adapt the training regimen. So this can guide to make sure that the learner is at their most optimal level throughout that skill acquisition process. So we can monitor the brain activity in the lab environment or even outdoors in low-fidelity environments. We can use complex technologies like VR headsets, stationary or on treadmill, or even actual environments like aviation is a key aspect because it provides this complex machine that we need to engage with. Or other technologies like humanoid robots, automation, AI is becoming more and more prominent. But it can be used with diverse participants, with children to elderly, right? And within the spectrum, and we can look at all these unique interactions, multi-individual, how different individuals come together, communicate, collaborate, and accomplish different tasks. The team effectiveness, teamwork, and this extends the diversity of the approaches. So we can look at the human experience. So I already mentioned about the aviation work, but we can use this for other technologies like assistive technologies, haptic feedback, different concepts that we can incorporate, or virtual reality. These are some examples of projects that we have accomplished over the years, but it can be also look at objects or things around us, like office equipment, or how we engage with food, or websites, messaging. So there are enormous number of options how we can use these technologies to better understand the human. So I want to just focus on a little more on assistive technologies, and I'm sure you're all thinking about how we can improve those focused on the assistive technologies, how we can improve the interface of these technologies. We want these to be more intuitive. We want to make sure that they require minimal cognitive effort, right? And we want the user experience to be high to truly provide the quality of life improvement that these technologies aim for. These are technologies that are intended to be used regularly. So here is an example from our lab where we applied neuroergonomics to wheelchair interface. And this was a collaboration with our colleagues in UK. And Shan Joshi, MD PhD student, performed this as part of his thesis. And we looked at different interfaces and were able to compare the cognitive effort in a controlled protocol where we manipulated the difficulty of the environment, the surface, and we looked at different interfaces, how individuals manage to tackle these obstacles. And we see that behavioral changes also across expertise, so that more experienced wheelchair users versus novices, they interacted differently in terms of the cognitive effort and the interface. So we described how this approach, this neuroergonomic approach, can be applied to further understand some of these intricacies. Another example that I want to bring up is the augmented or virtual reality headset. So as these technologies are becoming more prominent, there are a lot of questions. How do we perceive the world around us? How is working in VR different than in the real world? So here's a recent example, again, from our lab, where we looked at brain imaging in virtual reality and in the real world, where we compared the same task, problem-solving task, and we looked at the cognitive effort, the behavior, of course, and also how everything comes together, the neural efficiency. And we actually found that interesting, that the neural efficiency is highest in virtual reality when we compare the same task in the real world or in 2D computer screen. So now we can get these new insights that can guide also the design of these tools. So the list can go on and on. So from hardware user interface, like looking at buttons, and like the placement, does it provide this closed loop information feedback? Is the functionality of these buttons discoverable? So this is an example, actually recent project where we looked at the interface of coffee machines and compared different coffee machines, how easy it is to actually put together and use them. So these are just examples, and of course, from there to software user interface, like apps or websites or other technologies inside the computer, we can see the navigation structure or the visual design, or we can assess the overall, holistically, the cognitive experience of these complex interfaces. And this is an example from an investment tool that we looked at different components, compared new to the old design, and looked at different user groups as they engage this investment tool. So overall, I want to just highlight there are many things that we can gain by looking at the brain function. And of course, the primary is the direct access to the neural correlates of cognitive and emotional states. These are happening inside the brain, and if we can directly incorporate this information, and even in real time, we can get access to this information to adapt the entire experience, that can guide our next steps. And the other critical aspect that I want to highlight is this brain function data is complementary to the existing data, like behavior or additional information that we capture from physiology. So it's multimodal data needs to come together. So we need to put that in context, and we have different ways to incorporate them. And we talked about human to item interaction, but this can be expanded to human interaction. So instead of having this automation or device or item, what happens if we bring multiple individuals together? And that's also becoming a very exciting new research area. And we have been seeing this brain-to-brain interaction that causes predictable changes in the brain activities, like synchronization, for example. So one example is speaker-listener coupling, where a speaker like me conveying these abstract concepts from my head, as you listen and you process this information, we found that if there is this communication, as you process this information, the brain activities become similar across the individuals because becoming on the same wavelength. And if the communication is disrupted, then this similarity disappears. So this is the basis of many kind of follow-up studies, like looking at teacher-student synchrony, for example. Can we see if the student is really understanding and following? Or in clinical conditions, like can we see the early signs of autism even before behavior or even early on in the diagnosis range for high-risk individuals? So, but then it goes to team coordination. How do we work together more effectively, like in remote settings or in person? Can we quantify this additional information in addition to behavior? And behavioral data may not be available in many contexts, but we can use now brain information to get a more objective identification. So these were just examples, and I would like to just bring up this community that is growing. And we have been organizing International Neuroergonomics Conference Series with my colleague Frédéric Dohet. Started in Paris, France. We had in Philadelphia later. And we are seeing now it's growing, the attendance community. The last one was in Bordeaux. And some of the colleagues were here, attended. Hopefully, you will join one of these upcoming versions to get more information about neuroergonomics and how it can serve your needs or projects. Another aspect that I want to highlight is the academic journal. Because this research is growing at a fast rate, we put together with a group of colleagues this new journal that became the academic home for all neuroergonomists. And these are different sections within the journal. And now we have more than 350 experts from all around the world in the editorial board. And we are seeing still growing. And we have representation from all over the world. And hopefully that will be a fundamental kind of information source for many researchers and practitioners to identify how we can use these mobile neurotechnologies for real-world applications. And finally, I just want to finish by saying mobile neuroimaging is here, and it's only getting better. And we can see that these technologies can be used to better understand and measure the brain in not only lab, but in realistic settings. And we can capture meaningful information from them, like looking at cognition in diverse areas, and also different subject groups. And because these technologies are low cost and low operational cost, we can use them over time, again and again. So that gives us this longitudinal assessment, looking at the changes over time. And then, because they provide also in real-time information during even the interaction, this can be processed and feed back into a closed loop. That's the brain-computer interface. And we can see now new types of implicit or explicit PCIs that can be built. So it's with all your imagination. The platform technology is here. So hopefully it will grow with your contributions. So with that, thanks. And I would like to thank for the opportunity and see if you have any questions that I can answer.
Still have time, if you want to. Thank you very much, Professor Ayaz. Do we have any question in the room today for Professor Ayaz? Si vous voulez, il y a des micros dans les deux côtés de la salle. Levez la main et on pourra poser quelque chose. Yes.
I was wondering if you have experienced ethical problems to survey the brains of the young kids or babies. Thank you.
All right, thank you. Of course, the ethical considerations needs to be utmost. There is this whole field of neuroethics that evolved around 2005, again in Philadelphia, in a lot of colleagues contributing to that. And we need to, as technology developers also, we need to consider the responsible development. So these technologies that I described are non-invasive, that are non-harmful, that we can attach and detach without any risk to the individual. But eventually, we can imagine that future technologies that bringing a lot of detailed information, how that information is going to be used needs to be considered. And these are still open, and I would say we need better laws or regulations to identify like who owns the data from these and how data can be used, still not clearly defined. But at this point, the risk is minimal for any individual, even the children or babies. And in the clinical cases, this is done to understand and help the clinical population. All right.
Thank you. Do we have any other questions in the room? Yes, we do have one. Wait for the mic. It's coming for you.
Hello. Thank you. Yeah. Thank you, sir, for your presentation. Is there any side effects of using like red light, infrared on the brain?
Not that we know of, yeah.
Thank you very much for this is very interesting new technology. So the near infrared, what can it do more or less than the big machines like the fMRI?
Sure. So near infrared light this is like very close to our visible range. It's, first of all, I need to say it's already all around us. So in our everyday environment, from the sun, from the light bulbs, the electronic illumination that around us, we have near infrared light everywhere. So our body is constantly getting this near infrared light. And we are using this light similar, like if you have used like pulse oximeters, like you may have seen, like looking at heart rate, like at the fingertips, or like eye tracking equipment. A lot of these tools use near infrared light that is bombarding us, with that information. With FNIRS, we are using this on the scalp at much lower kind of intensity to look at these fluctuations that happen in the brain activity with this oxygenation changes. So that's a metabolic activity, and the same metabolic activity that fMRI measures. How neurons consume energy as they operate. We get these detailed big maps in fMRI looking at the same metabolic activity, but it is using the magnetic properties of the hemoglobin, deoxyhemoglobin particularly. In our case, we are using the absorption of hemoglobin, the light absorption, to capture the concentration changes, the same information in a different way. And we can get actually a more detailed time resolution with the FNIRS compared to those big machines, because we're literally using light, and that can go much, much faster than other things, right, that we know of. So it can measure very fast information, but the downside is it is limited to only the superficial areas, because light will not penetrate deeper areas. So only the outer cortex that is close to the skin level, the scalp level, right? But that is enough for us, because most interesting area for cognition and a lot of high-level executive functions are actually in prefrontal area or motor control, for example, primary motor area at the top. So these are the most interesting locations in any case. So there are always trade-offs with any technology. So we need to put that in context. Yeah.
One question for you. Thank you very much for coming to Montreal. It was thank you for your presentation this morning. And you know, at TechTwalab we also use FNIRS, and we've been informing many of our partners over the years of comparing different approaches using FNIRS and making decision about design. Coming back to the example we talked yesterday about your latest experiment, bringing FNIRS in the field is really complicated, and congratulations for the logistics of doing that. And what are concrete recommendations that you had for either the design of the interface for the in this project with the air flight controller, or maybe on the training of them? What would be, for example, of to the practitioner here is what can you tell them of improving the interface or the training of these people based on this research?
Yeah, it's a good point. So, I mean, I highlighted some examples, like, for example, one of our earlier work looking at the radar screen and the interface over there, or that can be similarly applied to the websites or any other tool, is we can get this general information about the holistic cognitive effort. How much an individual is working mentally to accomplish a certain task. That can be extracted from this information. And this is disassociated from the behavioral performance, because individuals can reach the same performance with different effort level. Imagine two students, they get both 100 over 100 in an exam, but one of them was just putting all the efforts trying to solve that question with every kind of concentration of attentional focus, and then the other without even breaking a sweat. So you can imagine that if the task was slightly more difficult, there could be different kind of outcome. And we can only see this if we look into the brain, if we look at the brain activity. So there is this complementary information that we get more in-depth insight. And we can look at now, expand this mental workload as this heterogeneous concept to cognitive and emotional state. The balance, like if this a pleasurable experience or if this creating arousal, high or low, all these different information can be triangulated from neurophysiological and physiological data to help better understand the interaction of the user. So that's the opportunity here. And because we get this continuous time series information, this information can be actually looked at each individual step. It doesn't need to be just one huge interaction. It can be looking at each individual step to better understand different aspects. Like, is there a roadblock, for example, in the navigation of the user as they go through from one place to another, or a series of tasks? Are they getting stuck at one location? And this is, again, going deeper from the superficial of behavioral data, but like failures can happen or missing information. But we're looking at now continuously what leads to that error. So we can pinpoint that additional information with this kind of data.
Right. Thank you very much. Do we have any more questions? We have time for one last. Yes, Jad, right here.
Thank you for this breathtaking presentation. Very, very sophisticated, advanced technology. My question is really going back to the heart of the questions that were asked in neuroscience, right? I had started in the field 12 years ago was when I was studying. That was actually how I got into working with the Tech 3 lab. They were interested in some of the research I'd done. By the way, for their recruitment, please apply because they're a great team, doing great work. Anyway, going back to the question, one of the conundrums at the time, again, this is 12 years ago, there's been a lot of advancements. The technology you're using is very cutting edge, and a lot has happened in the field, in that time. But at the time, one of the main questions that was still unanswered was the question of what is consciousness and where does it lie in the brain? And I have not been in contact much and up to date on what's happening. I think there has been some effort to go in that direction. And at the heart of your research, and we're talking about tasks and human behavior and day-to-day life, is the question of consciousness. So I'm very curious to hear your take on where you think this question is today and how your research moves us towards understanding that.
Well, excellent question. Thank you. This is actually one of the grand challenges of those whole society. It's outlined by IEEE. So how do we find that? That is such a grand challenge that I'm afraid we don't have much progress. We are at the same place. We don't have any details of how the brain actually accomplishes that amazing feat. But what we know is this information about this engagement with different tasks. So what we are measuring is we're at the very early stages of getting this catalog of mental states, which has been done in very specific artificial controlled tasks within the last 3 decades with the brain-computer interface and cognitive neuroscience fields. But with neuroergonomics now, we're taking that out of the lab, and we're looking at the brain on the go. And that expands that the grand mental state map that I showed you. We're still at the early phase of compiling that. Once we have that compiled, that can give us maybe the next steps, which is getting more specific information. So we have a long way to go. Yeah.
Thank you very much. Thank you. Thank you very much.